Now that we've discussed the properties of both exponential and logarithmic functions, we're now going to use those to build models for exponential growth and decay. All right, so we've seen the exponential functions before, namely functions that look like y equals c times a to the x. Okay, so in that function, the value for c, remember, is the y-intercept, and the value for a represents the factor by which the exponential function either grows or decays. All right, so a is the factor by which the function grows or decays. All right, so we've seen this before. The y-intercept is interesting because that gives you an initial value, a starting point. Okay, when your x value is 0, you plug in a 0, c is what you get out. Okay, so that's the point, 0 comma c. All right, so now what we're going to do is we're going to create two new formulas. And they're going to be, one's going to represent the growth of a population, specifically population growth. Could be bacterial growth, could be rabbits in a field, it could be any number of things, people in a country, but population growth. And the other is going to be decay, specifically half-lives. Okay, so a radioactive isotope that is decaying in half over a certain amount of time. Okay, so those two situations are going to be modeled by similar functions. We're just going to give different names to the variables. Okay, so for the population growth, we'll start there. So for population growth, the formula is going to be n of t, n being the number of, the number of organisms, could be bacteria, rabbit, whatever it is, people. Okay, the number, n for number. The number, and t is time in years, typically. And it's going to equal some initial value, we'll call it n sub 0, or some would say n naught, okay? And this n sub 0 is kind of like your c value here. It's your y-intercept, or your initial starting point. It's going to be followed by, or multiplied by, the base e. We're going to use the exponential, or the Euler number, as our base. And it's going to be e raised to the kt power, where k determines whether or not this is a growth or decay, and what the rate of which that growth or decay is. Okay, so in the past we were using the value of a primarily for our base, or the variable a, I should say, and that a value could have been either greater than 1 or less than 1. And remember, over in this, using this formula, let's not write a sentence here. If a was greater than 1, you had growth. And if a was between 0 and 1, you had decay. All right, so those two things occurred. But now we're using a base of e. Now e itself is greater than 1, hence the growth, right? However, the k value can actually change that. So the base, this a value, is really equal to the e to the k power. It's that entire expression of e to the k. E itself is greater than 1. It's, what was that, 2.71 or whatever that Euler number is. Why can't I remember that? 2.718, roughly, okay? But when you raise it to a power, if that power is positive, then this continues to be, growth. But if that power is negative, it flips that number over, right? It becomes 1 over 2.18. And then this thing, 2.718, sorry, 2.718. So 1 over 2.718 is actually less than 1 and becomes a decay. All right, so the K value, when K is positive, you get growth. And when K is negative, you get decay. All right, now we're specifically going to be using this for population growth. So we're going to be using K greater than 0 for this, all right? Okay, so that's for population growth. Now, for decay models, rather than using the same variables, we're going to change things up a little bit. So going back to this population growth, N is number of organisms, just defining everything. T is time in years. And N sub 0 is the initial value. Okay, that's your starting point. And of course the K is your, determines your growth rate. Okay. Now for the decay models, again, these are typically going to be in half-lives. Just means that whatever chemical you're measuring is going to decay in half over time, over a certain period of time. And different isotopes will have different half-lives or different decay rates, okay? And so with decay, we're going to use an A for amount. So the amount after time T is equal to the initial amount, so it's A instead of N. Instead of a number of organisms, it's the amount of the chemical, the isotope, whatever it is. And then we're going to have times e to the kt again. But here, we're going to be using a k value that's negative in order to get that to be a decay model. So here we're going to have k value, less than 0. Okay. Okay, so that should give us a pretty good idea of how these models are constructed. Now, your textbook makes mention of K being the growth rate itself. Okay, and so when K, and this goes for either situation, the decay or the growth, if K were, say, 0.45, if that were our K value, then your textbook claims that that's a 4.5% increase. Okay. Or 4.5% growth. Now that's not entirely correct. The growth rate itself technically is the value of e to the k minus 1. Okay, so technically it's e to the k, and then you subtract 1, I should say, from that. So e to the k, if k was 0.45, that'd be e to the 0.45 minus 1. Well, e to the 0.45, if you were to calculate that, is actually 1.046 and then some other decimals, 0.2786 minus 1. So the actual growth rate here is at 4.6%, right? The 1 gives you the growth. That means it's greater than 1, right? So it's a 4.6% growth rate. Oops. So you subtract the 1 off to get the actual rate. 0.046, or I should say approximately, which is a 4.6%. 6% increase. Okay, so it's not exactly the growth rate, right? So the K value and the actual growth rate are slightly different, even though your textbook seems to relate the two. And so if you're asked to give a growth rate based upon a given K value, just use that K value as a percentage. Otherwise, you can use this idea. If you're given the rate and you want to put it into the formula, you can use this idea to do that. We'll do a couple examples here in the next couple videos.